This lecture will be a quick summary of what we cover in AP Chemistry on the topic of voltaic cells. This is part 2 of the Chapter 20 lecture on electrochemistry. So we start describing what a voltaic cell is. Energy released in a spontaneous redox reaction that we balanced in the previous lecture is used to perform electrical work. And a voltaic cell or a galvanic cell is a device in which electrons that are transferred in this reaction can go through an external circuit and do some useful work. Now, voltaic cells are spontaneous redox reactions. And so here's a simple example of a voltaic cell. If you put a strip of zinc in a solution of copper sulfate, what will occur is that the copper will be deposited on the zinc, and then the zinc will dissolve into the solution, forming zinc 2+ ions. And the zinc is oxidized into the zinc ions by the copper ions, and then the copper is spontaneously reduced to pure copper by the zinc. So the entire process is spontaneous. Zinc spontaneously oxidized, copper is spontaneously reduced. Now, in order for the redox reaction to do useful work, we need that external circuit I mentioned earlier. And so the compartments need to be separated. These half reactions need to be separated from each other. And again, the electrons need to be able to flow from one half reaction to another via a wire. So here's the main parts of a voltaic cell. You have to have an anode where oxidation occurs. And in this case, there's going to be a chunk of zinc as one of the parts of the battery, and then there has to be a cathode compartment where the reduction occurs, and you're going to have a chunk of copper as one of the electrodes. Now there has to be a salt bridge which is used to complete the electrical circuit, and it allows cations to move from the anode to the cathode, and the anions go from the cathode to the anode. So it's pretty easy to remember which way the ions flow. So the cations flow to the cathode department and the anions flow to the anode compartment. And the reason they're flowing is because when you're losing these electrons, there will be a buildup of positive charge, and you have to neutralize that positive charge. And as you're gaining electrons, there's a buildup of negative charge, so again you have to neutralize that negative charge. Now, the two solid metals, the zinc solid and the copper solid, are called electrodes. The cathode is always positive and the anode is always negative, and here's the picture of it. So you can see the salt bridge in the middle. Now, the salt bridge happens to contain sodium ions and nitrate ions, and they don't affect the chemical reactions that are taking place, but the positive ions are flowing to the positive compartment and the negative ions are flowing to the negative compartment. So the cations to the cathode, the anions to the anode. Now, as oxidation occurs, the zinc turns into zinc ions, and the two electrons travel through the external wire, as we saw in the previous picture, and they flow towards the cathode, and they're going to be used up by the copper ions. So the copper ions will gain the electrons in the solution, then they'll be deposited on the copper electrode as the pure element copper. So the zinc electrode is actually going to lose mass because it's going to slowly dissolve into the solution to make zinc ions, and the copper electrode is going to get bigger and bigger because the copper ions in the solution are going to be turned into pure copper metal. Now the electrons, again, they flow from the anode to the cathode. That's from the negative to the positive. And the electrons cannot flow through the solution, so they have to be transported through an external wire. So the electrons can't go through the salt bridge, they have to go through the wire. The anions and the cations can go through this porous barrier or a salt bridge. And this is just another general picture of it without specific elements being listed. Now the anions and the salt bridge are moving into the anode compartment. Again, as I mentioned this before, it's to neutralize the excess zinc ions formed by the oxidation. And in the same way, the cations from the salt bridge are moved into the cathode department to neutralize the excess negative charge that are formed during the reduction. So here's a little summary. The anode is negative, and we say that it loses electrons, so it's called oxidation, and the anions in the salt bridge move towards the anode. And the cathode is positive, it gains electrons, it's being reduced, and the cations go towards the cathode compartment. And the electrons always move from the anode to the cathode. That's from the negative to the positive. So here's a way to remember which compartment is negative and which one is positive. We say ANO, which stands for the anode is negative in its oxidation, and then CPR is the cathode is positive reduction. And here is again another picture of what's taking place. The zinc turns into zinc ions and the copper ions turn into copper. So the anode is getting smaller and the cathode is getting larger. Now, the flow of electrons from the anode to the cathode is spontaneous, and I ask, what is this driving force? Well, this driving force is called electric potential energy. The electrons flow because there is potential energy for those electrons to move. Just like a rock will roll down a hill from a high elevation to a low elevation, the electrons are basically being pushed by this electric potential energy difference between the compartments. So the potential difference is the difference in the electrical potential energy in each compartment, and the potential difference is measured in the unit of volts. So volts is the driving force, it's the push. Now, the definition of a volt is the potential difference required to impart a certain amount of energy, that's 1 joule of energy, into a certain amount of charge, and the unit for charge is called a coulomb. And so the units for volts is actually a joule of energy per each coulomb of charge, and a coulomb of charge is simply a certain number of electrons. It's defined as 6.25 times 10 to the 18th electrons. And if you had 1 mole of electrons, the amount of charge would be 96,500 coulombs of charge, and that has been nicknamed a Faraday. Now, these constants for the Faraday are on the AP equation sheet. A Faraday is 96,500 coulombs per mole of electrons. Now, we will use this as a conversion factor at the very last slide of this presentation, so we don't have to worry about it right now, but these conversion factors are very useful in calculating electrolysis reactions. Now, EMF is another way of saying the force or the push or the voltage of these electrons through a circuit. So it's sometimes called electric potential energy, sometimes it's just called the voltage, or sometimes it's called the EMF or the electromotive force. So it has a lot of names. It's also sometimes called the cell potential. The cell potential is the EMF or the voltage that's produced by the two compartments undergoing a spontaneous redox reaction, and its symbol is E cell. Now, if a spontaneous reaction is occurring, then E is going to be a positive number, and if it's not spontaneous, it's going to be a negative number. Now, if you have the substances in the battery or in the cathode and anode compartments under standard conditions, which is 1 molar, 1 atmosphere of pressure if it's a gas, 25 degrees Celsius, you can call it E naught of the cell. That's the standard cell potential. Now, for the zinc copper battery, it's a standard cell potential of 1.1 volts. Now, the EMF of a cell depends on what substances you're using in the cathode compartment and the anode compartment, so it depends on the half reactions that are being used. If you're using, let's say, zinc and lead, it's going to give you a different E value. Now, in order to determine the EMF for a particular cell or the voltage of a particular cell, of a particular battery, let's say, you need to know what the E reduction potential of each half reaction is. So the standard reduction potentials, or E naught red, are measured relative to a standard. So they had to come up with a basic half reaction to compare all the other half reactions to. And the following half reaction has been picked. It's the hydrogen ion turning into hydrogen gas at 1 atmosphere of pressure, and the concentration of the hydrogen ions is 1 molar. And they came up with that standard, and they said, okay, we're going to call this half reaction E naught of the cell is going to be 0 volts. So everything else is compared to this standard hydrogen electrode, which is nicknamed SHE, or the SHE. So the SHE reaction is assigned a standard reduction potential of 0, and then all the other half reactions can be measured relative to the SHE. Now, the EMF of a cell can then be calculated from all of the standard reduction potentials that have been tabulated in your book, and here's just the simple formula that you do to calculate the voltage of a cell. You take the E naught reduction minus for the cathode minus the E naught reduction of the anode compartment. So you do the cathode E minus the anode E, the cathode minus the anode, otherwise known as the GER minus the LEO. So in this particular setup, we have the SHE compartment on the right side of the picture, where hydrogen is turning into hydrogen gas, and we have a zinc electrode turning into zinc ions, and you can see by the voltmeter reading it has a battery potential of 0.76, which means when you take 0 minus the negative 0.76, which is the reduction potential of the zinc, it's positive 0.76. Now zinc is oxidized, so since the cell's EMF is positive 0.76, that means the reduction potential for the reaction of zinc ions turning back into solid zinc would be a negative 0.76 volts. So zinc wants to spontaneously oxidize. So when you're writing this as a reduction potential, instead of zinc losing electrons, we have the reaction as zinc ions plus, or gaining 2 electrons, turning back into zinc. That would be a negative 0.76 volts, so it wouldn't be spontaneous. On the next page we just have the standard reduction potentials tabulated, and they're listed on this picture from the highest reduction potential, the highest E0 red values at the top, and then the lowest at the bottom. Excuse me. So the ones at the top really do want to be reduced. The ones at the bottom, since they're negative, they don't really want to be reduced. The reaction actually wants to run in reverse, so they kind of want to be oxidized. So anyway, in the back of our textbook that we use in Table E, they happen to be listed alphabetically. So here they're listed from most positive to least positive, but in our textbook they're listed alphabetically according to what the reactant is. So we're going to do a practice problem. It says the standard EMF for the following cell is 1.46 volts. This is indium ions going from +1 to +3 and bromine liquid going to bromine ions. Now we're going to calculate the E reduction potential, which is not in the back of our book, for indium going from +3 back to +1. So again, it has to be written as gaining electrons because it is a reduction potential. So we're going to break it up into 2 half reactions. We're going to list the LEO first and then the GER reaction. So we have +1 going to +3, that loses 2 electrons. Then we have the bromine gaining 2 electrons. Now we can look up in the back of the book the reduction potential for the half reaction of bromine turning into bromine ions, and it's a positive 1.06 volts. So we can just plug and chug the following numbers into our formula, the cathode reaction minus the anode reaction. So we have 1.46 being the total E0 of the cell. That equals 1.06 for the cathode reaction minus the unknown value. And so the unknown value ends up being a negative 0.40 volts. Now the reaction is spontaneous because we got a positive voltage, we got a positive E0 of the cell. And also indium went from +1 to +3 in the reaction. It was actually oxidized, so you might expect the value of the reduction or the reverse of that reaction to be a negative value. It didn't have to be, but it happened to be in this case. Now, if you change the coefficients of a half reaction, it does not change the E0 reduction potential. So it doesn't matter if you have 1 mole of zinc ions or 2 moles of zinc ions turning into the zinc solid. The E reduction potential is the same. And as you may suspect, the concentrations, since they're listed as 1 molar, the concentrations do change the E0 of the cell. They do change the EMF of the cell, and we'll see that later on. Now, the cathode reaction of a voltaic cell will always have the more positive E reduction value than the reaction at the anode. So in essence, if you had 2 reactions, let's say, or 2 half reactions, and they both have positive E0 reduction values in the back of the book, the one that's more positive will be the GER reaction, and the one that's less positive will be the LEO reaction. So in essence, what's happening is that the more positive cathode half reaction, the GER reaction, is forcing the other one to go in reverse. So if you have 2 of them that are competing over being the GER reaction because they're both positive, when you look them up in the back of your book or look them up in that chart that was on the previous slide, the one that's more positive will force the other reaction to go backwards. So when you do the GER minus the LEO, you'll still end up getting a positive value for the E. Here's a practice problem demonstrating this. Here's cadmium turning into cadmium solid, here's tin ions turning into tin solid, and we need to figure out which reaction is going to take place at the cathode and which is at the anode. So if you look up the E0 values in the back of your book, you can see that the reduction potential for the cadmium is negative 0.403, and the tin ions is negative 0.136 volts. So the one that's more positive will be reduced, that's the 10 ions, and the one that's more negative or less positive is the one that's going to be oxidized. So what is the value for the E naught of the cell? You do the GER reaction minus the LEO, otherwise known as the cathode minus the anode. So this will end up being a positive number, as we would expect, because it was spontaneous for a voltaic cell. Now we're going to look at the chart again, and I'm going to show you stuff about oxidizing agents and reducing agents. Now, you can use this table to determine the relative strengths of an oxidizing agent or a reducing agent by looking at the reduction potential values. So the one that's more positive is going to be a stronger oxidizing agent, and it's going to be one of your reactants on the left side of the equation. So the strongest oxidizing agent in this chart is the fluorine gas. The more negative the E reduction potential, the stronger the substance will be as a reducing agent, and it's going to be listed on the right side of the equation. So according to our chart, the strongest reducing agent will be lithium solid, because it has the most negative E naught reduction potential. So you can predict if one reactant can spontaneously oxidize another reactant. So here's again a visual of the strongest oxidizing agent and the strongest reducing agent. Now we're going to use this concept of EMF, which is the E naught of a cell, to calculate free energy, which we had in our previous chapter. So how does EMF relate to delta G? Well, here's the formula. Delta G equals negative NFE. If these are at standard conditions, you're going to have a very similar formula except a little naught value, so it's G naught and E naught. Now, N stands for the number of electrons transferred during the process. It's just a pure number. Like in our zinc copper battery, the number of electrons transferred was 2. The F stands for the Faraday constant, which is 96,500 coulombs per mole, and E is the cell potential in the units of volts. When you do this calculation using number of electrons, coulombs per mole, and volts, G is going to be in units of joules per mole. Now, usually it's given in kilojoules per mole, so you can divide it by 1,000 if you want to keep it in kilojoules per mole. Now, since N and F are positive numbers, then when E is a positive value, this formula will make G a negative value, and so it's going to be spontaneous as we would expect. So E is positive when it's spontaneous, and G is negative when it's spontaneous. If the reactants and products are in their standard states, then we just add the little zero, the little naught sign, and everything works out fine. Now, the Nernst equation is the next equation that we have to tell you about, and it deals with a chemical reaction that's not at standard conditions. So a voltaic cell will function until E is equal to 0. At that point, equilibrium is reached. So at the point at which equilibrium is reached, the E value equaling 0 can be determined by the concentration of the reactants and the products that are involved in the redox reaction. And the Nernst equation relates the EMF to the concentration of stuff in the anode compartment and the cathode compartment. Now, the stuff in these anode and cathode compartments have to be either aqueous or gases in order to appear in this Nernst equation. Solids, that would be the electrodes, do not affect the EMF of cells. So you could have a small electrode or a big electrode. It's not going to affect the EMF. It might affect the life of the battery, but it's not going to affect the amount of volts that come out of the battery. So here's the formula. We have E, which stands for the cell potential not at standard conditions, and that equals E naught minus RT times the natural log of Q divided by N and F. R stands for the constant 8.31, T is the Kelvin temperature, Q stands for the reactant quotient, or the products divided by the reactants raised to their stoichiometric coefficients in our balanced equation, and again they have to be aqueous or gases to appear in Q, and N stands for the number of electrons, and F is the Faraday constant. Now, if you want to express this as log base 10 instead of a natural log, your formula changes a little bit, and you can see the derivation in the textbook that we use. Now, sometimes the temperature is given as 25 degrees Celsius, so it makes it a little easier to already plug in the R value, plug in the temperature in Kelvin, and you get this formula, which is used a lot in your homework and practice problems. And I believe this one is also on your AP equation sheet. So it just gets simplified a little when they plug in the constants R and then T, and F as 96,500. So let's see how the equation can be used. Here's a zinc copper battery, and we usually know it's 1.1 volts, but if you're not at standard conditions, let's say the concentration of the copper ions is 5 molar and the zinc ion is only 0.05 molar, well, what's that going to do to the voltage? So we're going to do products divided by reactants, and we're going to see what happens. When you plug them into your formula, you're going to get the log of a number less than 1, and then you're going to multiply by 0.0592, and you're going to divide by 2, which is the number of electrons that are being transferred, and you're going to end up getting a little higher voltage, because when you take the log of a number less than 1, you're going to get a negative value, and you're minusing a negative. So the voltage goes up 0.06 volts. So it's a little more. Now we're going to talk about something called a concentration cell. Now the Nernst equation shows us that using the same species in the anode and cathode compartment of a cell, but at different concentrations, can actually generate a voltage. So for example, if you have a nickel anode and a nickel cathode, but the compartments are at different concentrations, this reaction will proceed until the concentrations in both compartments are the same. So the anode compartment is going to go from light green to darker green, and in the cathode compartment it's going to go from darker green to lighter green. And you can actually calculate the amount of voltage that it produces depending on the concentrations that are in the anode and cathode compartment. As long as the concentrations are unequal, a voltage will be generated, and in this particular picture it's 0.0888 volts. And so we can look at the formula for calculating Q. Now, in order for a voltage to be produced, we know that Q has to be a negative number, because you're going to be subtracting a negative number. So we're going to be taking the log of a number that's less than 1. So that's what I meant. You're going to have to take the log of Q, which needs to come up with a negative number. So basically what that means, in a nutshell, is that you're going to take the diluted solution's concentration divided by the concentrated solution. So you always do dilute divided by concentrated. So you're going to do the 0.001, which was our example on the previous page, divided by 1, and you'll get the 0.0888 volts. So it's always dilute over concentrated, which is, again, the product over the reactant. Now, it's very important to understand that the E naught of a concentration cell is 0, because it's the exact same reaction as the anode and cathode compartments. One you have nickel turning into nickel 2 plus, and the other you have nickel 2 plus turning into nickel. So you don't really need to look up the nickel's reduction potential in the back of the book, because you're going to do whatever the number is for your GER reaction minus whatever that same number is for the Leo reaction. So anyway, the point is that when you use a concentration cell, please make sure you plug in 0 for E naught. It's always 0 for E naught in a concentration cell. And the only thing that's going to affect the voltage is the concentration of the two compartments. Now when the compartment reaches equilibrium, the EMF is equal to 0. And a pH meter functions on this principle. Basically what a pH meter does is it takes a compartment that has a certain concentration of hydrogen ions, you stick that probe down into your unknown solution of another concentration of hydrogen ions. The difference in the concentrations of your little compartment in the pH meter with your unknown solution, the difference in those concentrations creates a little bit of voltage, and that voltage is translated into a pH. And your heart beats on this principle, because inside your heart there might be a different concentration of calcium ions or sodium or potassium ions. I'm not an anatomy teacher, but it's described in our textbook. But basically there's a different concentrations inside some cells in your heart versus outside those cells, and it creates a jolt of electricity, and that makes your heart pump. Now, cell EMF and chemical equilibrium can be compared in a formula, and we'll derive that formula right now. So a voltaic cell is functional until E equals 0. At that point, you have an equilibrium established in the reaction, and then the cell is dead. And when the system's at equilibrium, we know G is equal to 0. So from the Nernst equation, at equilibrium at 298 Kelvin, which is again 25 Celsius, your standard values, then E is equal to 0, and then Q is equal to K. So you can plug in E equal to 0 because your battery's dead, and that equals E naught of the cell, the original E value at standard conditions, that is minused from an RT divided by an NF, and then you have the natural log of, instead of Q, you have K. So you can simplify this equation at 25 degrees Celsius and solve for the equilibrium constant, and you get this formula. So if you know the E naught of a cell, you can actually calculate the equilibrium constant when the battery is dead. So if you know E, you can calculate K, or if you know K, you can calculate E. Now the next part of the notes deals with batteries and all their properties, but that's in the second packet of notes, so I'm going to stop the lecture here and continue that other lecture in part 3.